Welcome students, welcome to today's All 4 e-learning session. Today we are going to start with the next topic in heat. That is, in the previous classes we have studied about the temperature, measurement of temperature, different scales of temperature, etc. Now let us move on to the next topic called thermal expansions. The next chapter is known as thermal expansions. Thermal expansions. What do you mean by thermal expansion? Expansion is the word which indicates an increase in the dimensions of the body. It represents an increase in the dimensions of the body, and it is caused by thermal expansion. That means an expansion produced in a body because of heat energy supplied or increase of temperature. Whenever we are heating a body, we are giving heat energy to the body so that the temperature of the body will increase. As a result, there are some expansions in the body. So these expansions increase in the dimensions of the body, like increase in length, increase in area, increase in volume, like this. So these are produced by a change in temperature by supplying heat energy to the body. That's why we call it as thermal expansions. In thermal expansions, we can study about the expansions of solids and liquids and also gases. In all the three states of matter, we can see expansions. So expansions are possible in solids, liquids and gases. In all the three states, we can study about the expansions. As we said, expansion is an increase in the dimensions of the body, and these thermal expansions are caused by an increase in the temperature of the body. So out of all the three types of expansions in solids, liquids and gases, first let us start with the expansions in case of solids. Expansion in solids, right? Thermal expansions of solids. When we consider solids, or let us consider a matter. As we know, matter exists in three possible states of solid, liquid and gas. Consider a cube of ice cube. When we are supplying heat energy, that will melt into water. From solid state to, it is converted into water which is present in the liquid state. When still we are supplying heat energy, that will be converted into water vapor which is present in the gaseous state. So it is initially present in solid state and converted into liquid state and then converted into gaseous state. So in this case, what is happening here? What is happening here? In solid state, the molecules are very close, or atoms are very close. We say intermolecular distances are very close, very less. And here intermolecular distances are moderately increased. When it is moderately increased, you will have the liquid state, and gases, the intermolecular distances are largest. Largest intermolecular distances are present in the gas, and because of minute or very small intermolecular distances in case of solids, solids are characterized by a definite shape, a definite size. But coming to liquids, there is no specific size for the liquids. Liquids will take the shape of the container in which they are present because the intermolecular distances are large. And coming to the gases, intermolecular distances are still more increased, and we don't have any specific shape and size, and whatever volume of the container you take, the entire volume is occupied by the gases, so that volume of the container is the volume of the gas. You cannot have any specific volume for gases, but in liquids we can have specific volume. Whatever may be the container, shape may change, but volume remains in case of liquids. But in gases, we don't have any volume specifically, and whatever volume of the container is present, in which gas is present, that represents the volume of the gas. So in all the three states we study the expansion, but here intermolecular distances are very small. If we consider 1 cubic centimeter of a solid, that means we consider a cube of dimension 1 centimeter. In case of solids, that will contain around 10 power 18 to 10 power 21 number of particles. When the 1 cubic centimeter is containing so many number of particles like this, of the order of 10 power 18 to 10 power 21, we can understand how close the particles are. How close the particles are, we can understand from this. That means in case of solids, the particles are very close, and because of this close packed structure, solids are specified by a fixed dimension. It will have some regular, irregular shape. Liquid solids are characterized by a well-defined structure. They will have some lattice structure in case of the solids which are called crystalline solids. In case of crystalline solids or metals especially, they are having a specific geometric structure. But all this physical fixed dimensions and fixed geometrical structure, all this is possible in case of solids because of the small intermolecular distances. And now these intermolecular distances will be increasing to produce an expansion in case of solids. Now to study about the expansion of the solids in details, first let us know what is the basic reason for the expansion of the solids. At any temperature, let us say T degrees centigrade, or even at the room temperature, solid particles, even in case of solids, all the particles are associated with some amount of kinetic energy. And you know, the kinetic energy is produced in a body because of motion of the particles. So at any temperature, all the particles in a solid, they will have some kinetic energy. But how the particles can have kinetic energy when the solid is at rest? Solid may be at rest, but the particles inside the solid, they execute a motion because of which they possess kinetic energy, and this motion is a vibratory motion. It is a vibratory motion. You can have kinetic energy for a body in case of any type of motion, either translatory or rotational or vibratory motion. But in case of solids, translatory motion is not possible because they are bonded by intermolecular attractions. And similarly, sometimes rotatory motion is also not possible in some cases. But in general, in all the solids, they can execute vibratory motion. So practically, every particle, keeping their intermolecular distances or interatomic distances a constant, they can vibrate at low temperatures when the energy is low. So that every particle, because of the intermolecular attraction, they possess some potential energy. They possess some potential energy. Remember that in physics, in any case, when the attractive forces are developing potential energy, or work is done because of attractive forces, the potential energy is always negative. As a result, if we draw a graph between intermolecular distances and potential energy because of intermolecular attractions at very low temperatures, the graph between potential energy and intermolecular distance for the particles will be symmetric like this. That means if this is the mean position of the particles in simple harmonic motion or vibratory motion, we know if you consider a particle here, when it is executing simple harmonic motion, it will be moving between two extreme positions. This is mean position, this is one extreme, this is another extreme. You can have an example of a pendulum. When pendulum is moving from the rest position, it will be moving between the two ends, and these two ends we call it as extreme position. In normal condition or at low temperatures, both the extreme positions will be at the same distance, and the particle will be executing from one end to the other end like this. And in case of a solid, when the particles are executing simple harmonic motion or vibratory motion, the intermolecular distances, suppose this is the origin, we are measuring the intermolecular distance like this, so that the intermolecular distance at any position is a constant, so that the particle will be moving from one end to the other end. It may move between these two extremes. So that at any position, if the displacement is x here, this is also x, so that the intermolecular distance will be the same at low temperatures, so that the potential energy curve is called a symmetric curve. A symmetric curve is possible like this, so that at any position, at any temperature, intermolecular distance will be the same, and which is possible only at low temperatures. But when the temperature of the solid is considerably increased, what happens? There will be a asymmetry developed in the potential energy curve. What do you mean by asymmetry? Here you can see intermolecular distances are almost remaining a constant. From the origin, we are measuring the intermolecular distance, and this intermolecular distance is remaining constant like this. But practically, at very high temperatures, there will be a considerable change. There will be a considerable change in the distance between the interatomic distance between the molecules. Let us see how it will happen. If you draw a similar potential energy curve, taking the intermolecular distance on the x-axis and potential energy on the y-axis, the graph will be like this. The graph will have a change like this, so that suppose at a lower temperature, say T1 or T1 degrees centigrade, let the potential energy of the particle is E1. E1 is the potential energy at a temperature T1. So that this is the mean position, so that the average distance, let us say this is O, and the particle is at a position, let us say A. So it will be moving from between the positions A1 and B1, and A is the mean position of the particle, so that it will be moving between the 2 points A1 and B1, so that interatomic distance will be changing between OB1 and OA1, so that it is moving between these two positions, and the average distance, interatomic distance, will be equal to OA. OA is the average interatomic distance, and particle, because it is executing simple harmonic motion, it is moving between the two ends from B1 and A1. So it can move from A to B1 and again A1. Between these two positions it is moving. But now at very high temperature, when the temperature is changed, suppose to a temperature, let us say some T2 degrees centigrade, there is a considerable increase in temperature. As a result, what happens is, on either side amplitude remains the same, so that the position of the average distance of the particle from the mean position, it is changed like this. So let us say now the particle is present at its new position, let us say some A dash. So it will be moving from A dash to this new position, and this is the another extreme. Between these two extreme positions, the particle is moving. But if you consider the average distance or average interatomic distance, that moves from O to A dash. So from the initial interatomic distance OA, now at a higher temperature T2, we can say the average interatomic distance is O to A dash. Very clearly, OA dash, which is the interatomic distance average value at the temperature T2, is clearly greater than the average interatomic distance at the lower temperature T1, which is OA. So OA dash is very much greater than OA. That means clearly the interatomic distance is increasing when compared with the initial condition. And this cause of increase in the interatomic distances, that is, the cause is the change in temperature. But as an increase of, because of an increase in temperature, there is an increase in the interatomic distances. Very clearly, interatomic distance here, it is remaining constant at very low temperatures. But corresponding to a change in temperature, there is an increase in the interatomic distance here. Initially, it is only OA. Now it is OA dash. So it is moving from O to A dash. This is responsible for an increase in the interatomic distance, and this causes an expansion in the solid. So an expansion is produced by an increase in the interatomic distances, and as a result there is an asymmetry developed in the potential energy curve like this. So practically what we say is the expansion of the solid is due to an asymmetry in the potential energy curve, and this asymmetry causes an increase in the interatomic distances, and as a result the solid will expand. So this is the basic reason for the expansion of the solids, right? Now after knowing the reason, what is the basic reason here? Increase in temperature is responsible, and because of increase in temperature the potential energy curve is becoming asymmetric, and because of which there is an increase in the interatomic distances. As the particles are moving away, the interatomic distance is increasing, so particles will move away. So initially if we say that the solid is like this, suppose this is the solid like this, there are two particles present with this much of distance, but now the distance between the particles is increasing. As the distance between the particles is increasing, the dimension of the body will also increase. So when compared to this one, there is an increase in the interatomic distance, thereby the solid is also expanding, and this is the what we call it as a thermal expansion of the solids. So very clearly the increase in the dimensions or increase in the interatomic distances is caused by change in the temperature of the body, and that we call it as thermal expansion. Now let us go into the details of thermal expansion. Now we have understood about what is the reason for the expansion and how it is happening, we studied. Now let us go to the expansion details in a solid. Very clearly, because of increase in temperature, there will always be an increase in the dimensions of the body caused by an increase in the interatomic distances. In case of solids, depending upon the shape of the solid, we can study three types of expansions. We should not misunderstand that there are three types of expansions. Expansion is always of the same type. Expansion is always of the same type. There is a unique type of expansion. It is always unique. But depending upon the shape of the body, we can study three types of expansions, or we can understand that we can study the expansion in three different ways in case of solids. For example, let us consider a wire. Let us consider a wire like this at some temperature T1. When the temperature is increased, for a wire like this, the dimension is length, because area of cross section is very small, the volume is also small, so that the dimension which we can consider is only length of the body. So when there is a change in temperature, there will be an increase in the length of the wire, so that at the low temperature T1, let us say length is L1. When the temperature is increased to T2, length will also increase. Let us say there is an increase in the length of the wire. Then we say it is called linear expansion, or an expansion in the length of the wire. An expansion of the length of the wire because of increase in temperature, that is called linear expansion, or an expansion of length. When the body is having only one dimension like this, then we can say that there is an increase in the length of the wire, or there is only linear expansion. But now let us suppose the body you have taken is a two-dimensional body. Let us consider a plate like this. Let us consider a plate like this. It is having a length L, breadth B at the room temperature. Now when you increase the temperature, what happens? Because of increase in temperature, length of the body will increase. The breadth of the body will also increase. As a result, there is a linear expansion along the length. There is a linear expansion in the perpendicular direction in the breadth. As a result, the total body will be increasing to a dimension like this. As the body is increasing in the dimension, both the dimensions, clearly the final length, let us say L dash, and final breadth is B dash. So there is a linear expansion along the y-axis, you can say, and there is a linear expansion along the x-axis also, so that breadth is increased, length is increased. There are linear expansions in the two perpendicular directions like this, but as a result, there is an increase in the area of the body. Initial area of the body L into B. The final area, if you say A2, it is L dash into B dash. Very clearly, length is increased, the breadth is also increased, so that there is an increase in the expansion area also. So here we can study linear expansion in both the directions and also aerial expansion also. So because the body is two-dimensional here, we can study expansion of length or linear expansion in two perpendicular directions along the x-axis and also y-axis, and this produces a change in area. This produces a change in area, so that there is an aerial expansion also. So in a body having two dimensions, we can study linear expansion and we can also study aerial expansion. So here we should not misunderstand that the body is having two types of expansions. Body's expansion is only unique, but because the body is having two dimensions, we are able to study the expansion of length along the y-axis and also along the x-axis. So an expansion along the x-axis produces an increase in the breadth, and linear expansion along the y-axis produces an increase in the length, so that totally as a whole the area is increasing. So here we study linear expansion in each direction, and totally in the body we can study aerial expansion also. So here in two-dimensional body we can study about two types of expansions, in the length and in the area also. Now if it is a three-dimensional body like a cube, when you consider a three-dimensional body like a cube, what happens? Suppose it is in the form of a cube like this. Then when you are increasing the temperature, there will be an increase in length, there will be an increase in breadth, and there will be an increase in we can say this height also. Let us say this is length, and this is breadth, and this is height, because we use in three dimensions the notation like length, breadth, height. So we call this as height instead of length, and we call this as length, and this is breadth. There will be, because of increase in temperature, there is an increase in length, there is an increase in breadth, and there is an increase in height also. Then what is happening? As a whole, length, breadth, height are increasing, so that if you consider this face if you consider, height is increasing, length is increasing, area will increase. For each face, if you consider the face here, the length and breadth are increasing, so there is an increase in area of this face, and as a whole, as length, breadth and height are also increasing, there will be an increase in the volume of the body also. So totally you can study linear expansion along the three dimensions, three directions along x-axis, y-axis and z-axis, and in each phase you can study about aerial expansion. And as a whole, if you consider the volume of the body, initial volume, length into breadth into height, let us say V1, and final volume of the body is L dash and B dash and H dash. All these are increasing in the dimension values, so the final volume is also increasing. So as a result, we can study about linear expansion in each direction and aerial expansion for each face, and finally volume expansion as a whole in the cube. So totally there is a three type of expansions we can study in case of a three-dimensional body. So in one-dimensional body we can study only about linear expansion, an increase in the length. In two-dimensional body we can study two types, the expansion in two directions, that is linear expansion along the length, linear expansion along the breadth, and apart from that we can study about the aerial expansion also. And coming to the third one, when the body is three-dimensional, in each dimension we can study about linear expansion, that is expansion of length, expansion of breadth, expansion of height, and for each phase we can study about the aerial expansion, and finally as a whole in the cube we can study the volume expansion. So depending upon the shape of the body, we can study either one linear expansion or linear and aerial expansions, and finally in the three-dimensional body we can study all the three types of expansions, linear, aerial and volume expansions. So this is about the basic idea about the expansions of the body that we can study, and in this class we have studied about the three types of expansions, and in the next class we will study about each expansion and the measurements, how we can study about the expansions, because all the bodies do not expand equally. For the same change of temperature, some bodies may expand very large and some bodies may not expand that much. So what is the difference? How to measure the expansions in each case, about linear expansion, areal and volume expansion. And when there is a change in the volume, you know, when the mass of the body is remaining constant, there will be a change in the density also. So all these mathematical calculations and the related coefficients of expansion we study in the next class. So let us stop here.